Hey everyone, I'm really excited about Lecture 34A. A lot of interesting topics where we're really going to apply our differential equations and linear algebra knowledge to three main situations. We're going to look first at a trapping region for a system in polar coordinates where it's fairly easy to understand what's going on in polar coordinates. We'll convert it to rectangular coordinates where it's harder to understand, but the polar coordinates will still be helpful. It's an easy application ultimately of the Poincare-Bendixson Theorem to prove there exists a periodic solution inside this trapping region. In 35A, we'll look at a more complicated example. We'll also look at a Lyapunov function for a linear system with a real sink at the origin. It will be an application of quadratic forms that we've been talking about in the B lectures. Then at the end, we will introduce the idea of Laplace transforms, our last main topic in the A lectures. That will continue to be our main topic actually in 35A, 36A, and 37A. But we will continue with some other stuff as well. All right, so what is the simplest way to create a system with a single attracting periodic solution called a limit cycle? If you try to think about systems of differential equations in x and y in rectangular coordinates, it's really hard to come up with an example. There are examples out there, you can find them, like the Van der Waals system. However, it's definitely hard. It's much easier if you use polar coordinates right out of the gate, and that's what we're going to do here. In the last lecture, 33A, we considered an example that had a non-hyperbolic equilibrium point at the origin, and we used polar coordinates to help us understand what was going on there. Here, we're going to start with a system in polar coordinates that clearly has an attracting periodic solution, or limit cycle, and we'll convert it back to rectangular coordinates where it would be less clear that it's going to have a periodic solution. The existence of the attracting periodic solution, again the limit cycle, can also be proved with the Poincare-Bendixson theorem from lecture 31A, though it's really not needed here, it's just to illustrate it. It's a fairly simple application in this case. Here is the system in polar coordinates. dr dt and d theta t equals some functions of r and theta. The right-hand side of the dr dt equation is r times 1 minus r, or r minus r squared. And the right-hand side of the d theta dt equation, g, is a constant function, the constant function 1. That's pretty easy to think about. That means theta is increasing at a constant rate of 1 radian per unit time. Whatever the solutions are doing, they are, at least if you're not at the origin, you're going around the origin, and the angle is changing at a rate of 1 radian per unit of time. Constant rate. So there's some cycling going on here. What about the dr dt equation? If you think about the graph of this right-hand side function, which is, doesn't depend on theta, think of it as a function of r. When r is positive, we don't want to think about when r is negative here in polar coordinates, at least in this simple kind of situation. We got r times 1 minus r minus r squared. That's a graph that's an upside down parabola with intercepts at r equals 0 and r equals 1. It's going to look like this. In other words, dr dt, the rate of change of the radial coordinate with respect to time, is positive when r is between 0 and 1. R is increasing, the point is moving further away from the origin, and negative when r is bigger than 1. dr dt is negative, the point is moving closer to the origin. So the circle of radius 1, in fact, is a periodic solution. It's pretty easy to see that here. When r is 1, dr dt is 0, and d theta dt is 1, you're going to be moving around the unit circle at a speed of 1 radian per unit time. You'll go toward the unit circle when r is between 0 and 1, but you'll go also toward the unit circle with r decreasing when r is bigger than 1. You should be able to see, because of what I just said here, that the phase plane in the xy plane will have a periodic solution that is the unit circle of radius 1. Again, theta is increasing over time. Solutions are going to approach it from either side. It's going to be an attracting periodic solution, a limit cycle. What about at the origin? When r is 0, you're at the origin, dr dt is 0. There's actually an equilibrium point at the origin. So that's what it would look like in the xy plane. You actually can think about this in an r theta plane, if you wanted to. In the r theta plane, where r and theta are your rectangular coordinates, this would have vertical straight line solutions at r equals 0 and at r equals 1. And in between these two, your solutions are going to look like this when r is between 0 and 1, and your solutions are going to look like this when r is bigger than 1, something like that. And the idea here of transferring from this coordinate system to this one is that these solutions get mapped onto these solutions. That's another way to think about it. Not absolutely necessary, but you can think about it that way if you wanted to. The solutions get mapped, well, at r equals 0 gets mapped to an equilibrium point at the origin, and at r equals 1 gets mapped to a periodic solution on the unit circle. How about converting to rectangular coordinates then? How do you do that? We did it, we converted from rectangular to polar last time in lecture 33a. Now we're converting from polar to rectangular. We're going the opposite direction. We need these conversion equations, which come from trigonometry. X equals r cos theta, y equals r sine theta. In the last lecture, we used r is square root of x squared plus y squared, which we will use again here in a minute. And we also use the fact that tangent of theta is y over x when x is non-zero to help us do the transformation. Here we use these equations. We also do use the fact that r is the square root of x squared plus y squared. What are we going to do? We're going to try to find the differential equations for x and y in terms of t. We need to differentiate these equations with respect to t. Keep in mind r and theta depend on t, so x and y depend on t. So when you differentiate, you need the product rule. You also need the chain rule. In the first case, dx dt, focusing on this equation here, that's the product of two functions, r and cos theta, where r depends on t and theta depends on t. It's really an r of t times cos theta of t. So we take the derivative of the first function, dr dt, times the second function, cosine of theta, plus the derivative of the first function, plus the first function, r, times the derivative of the second, which includes the minus sign. Negative sine theta d theta dt is the derivative of cos theta with respect to t, keeping in mind that theta depends on t, so you need the chain rule to get an extra factor of d theta dt there. That's always tricky for people. You've got to be careful. Now we want to convert this to completely in terms of x and y, which you can see we've got at the end. How do you get there? dr dt from the previous slide is r minus r squared. d theta dt is 1. That's 1. So this simplifies to this. Expand this out, multiply the cosine through, you get r cos theta minus r squared cos theta. The r cos theta is right there. The minus r squared cos theta is right there. I've purposely written it as r times cos theta, because now I can convert back to x and y. R cos theta equals x, minus r sine theta equals minus y, and minus r times r cos theta. The r cos theta right there, that is the same as x, and the r is the same as square root of x squared plus y squared. And you can see in looking at this now, that final expression, x minus y minus x times square root of x squared plus y squared, it would be difficult to come up with this if you didn't think about polar coordinates to begin with. And it's similar with the dy dt equation. Here are the details. Derivative of the first function times the second function, plus the first function r. Cos theta d theta dt is the derivative of sine of theta with respect to t, using the chain rule. Once again, dr dt is r minus r squared, d theta dt is 1. Multiply through simplify, replace r cos theta with x, replace r sine theta with y, replace this thing with y, that's a y, r sine theta times r, which is the square root of x squared plus y squared. Yeah, you look at this, probably have no idea there's a periodic solution until you get Mathematica or some other program to graph solutions for you. I did. Here's the phase plane, which I tried to draw on the board right here. In the xy plane, I'm about to show you. I added nullclines. I also added a trapping region to the picture. And the limit cycle is clearly seen. There we have it. The blue arrows represent solution curves. The pink and brown curves represent nullclines. This pink one, or the brown one, let's look at first, is the x nullcline. You can see solutions are crossing that vertically. that's where this thing equals 0. Looking at that thing and setting it equal to 0, you'd have no idea it looks like this brown curve. It does. The pink curve is the y nullcline. You're crossing horizontally here and down here. Setting that equal to 0, solving for y as a function of x can't really be done, but you can use the computer to program and graph this pink curve that you see. Where brown and pink intersect, you've got an equilibrium point at the origin, and this yellow region with a black boundary is a trapping region. Solutions are going directly into the trapping region along the boundary. That's the outer circle of radius 3/2 and the inner circle of radius 1/2. The red curve is a solution curve. I made an initial condition close to the origin there. It's going away from the origin and approaching the limit cycle, the attracting limit cycle at radius 1 as time goes by. And along the inner part of the trapping region, you also have solutions going in. It is indeed a trapping region. You could say by the Poincare-Bendixson theorem, since this trapping region has no equilibrium points inside of it, because the only equilibrium points of this are 0, converting back to polar coordinates is the easiest way to see that. The only equilibrium point is at the origin. There must be a periodic solution inside of it. That's what Poincare-Bendixson tells you. You don't really need it in this case because the polar coordinates tell you definitely you have this periodic solution at r equals 1. But it's nice to know that Poincare-Bendixson theorem can be used if you wanted to. How about some details to verify that this is really a trapping region? You can see it visually. Those blue arrows again are going into the trapping region along both pieces of the boundary. It should be a trapping region. Is there a way to confirm that? What I'm about to show you confirms it using what are called normal vectors. We're going to take an arbitrary point along the boundary, say for example right there. Along the outer boundary, we'll look at what's called an outward pointing normal vector. We'll take its dot product with the vector field at that point, and we'll see that we get a negative number, meaning the angle must be bigger than 90 degrees. And that confirms the vector field is going in along the boundary, and it doesn't matter where you pick the point. Along the inner circle, pick an arbitrary point, we'll look at an inward pointing normal vector, take its dot product with a vector in the vector field. Once again, the angle is bigger than 90 degrees, and that is going to confirm that it is a trapping region. We'll get a negative dot product confirming that the angle is bigger than 90 degrees. So let's be precise. We're going to define and verify the trapping region. Here is our proposed trapping region. S is the sum of all points such that x squared plus y squared is between 1/4 and 9/4. 1/4 is 1/2 squared. 9/4 is 3/2 squared. I picked those for a reason. Those are the inner and outer boundaries where x squared plus y squared equals 1/4 and 9/4. You can think of it in terms of the polar coordinate r. We are looking at the region between two circles centered at the origin of radius 1/2 and radius 3/2, including the boundary. This is a closed and bounded compact trapping region. But why? Let's confirm the dot product computation. For an inward pointing normal vector along a circle of radius r, this ny here is my inward pointing normal vector, negative x, negative y. Why is that inward pointing? Because it's the opposite of the position vector of the point. If we're talking about a point xy, its position vector points from the origin to it. If I negate that, put negative signs in front of it, it points directly toward the origin. That is an inward pointing normal vector. This dot product should be negative when r is less than 1, so that I'm on the circle of radius 1/2. Check this calculation. X times y terms cancel. You can write everything in terms of the polar coordinate r. You can ultimately factor like this. And that is indeed negative when r is less than 1, in particular when r is 1/2. Okay? And we only care about positive r's. That confirms along the inner boundary that the vector field is pointing into the trapping region. What about the outer boundary? We got to use an outward pointing normal vector along a circle of radius r. In our case, r is 3/2 in this case. N of y is this vector. It's the position vector of the point itself. from the origin to the point itself, although if you're going to imagine it in the picture that I drew on the previous page, if you based it at the point itself, it would look like that. It's still in the same direction, it still has the same length. Most importantly, it's got the right direction. It's pointing out of the trapping region. I take its dot product with the vector field, I get a negative quantity again. This quantity here is negative when r is bigger than 1, and in particular when r is 3/2. It's bigger than 1. Okay? Choosing r to be 1/2 and 3/2 was somewhat arbitrary. Here I could have picked any r between 0 and 1. Here I could have picked any r bigger than 1. But those are kind of the nicest numbers to pick between 0 and 1 and bigger than 1. I mean, I could have picked 2 there, I suppose, but I wanted it to be closer into the solution curve in the picture. Therefore, S is a trapping region. It also has no equilibria in it. Polar coordinates is the easiest way to verify that. And actually, well, we're looking at the picture and seeing the nullclines where they cross, only at the origin. Therefore, by the Poincare-Bendixson theorem, you can say S has a periodic solution inside itself. Okay? Technically speaking, this is a pretty trivial application of Poincare-Bendixson. You don't really need it. The polar coordinates is enough. Again, in lecture 35A, I want to look briefly at a more complicated application, just giving the main idea without getting into a ton of details like this, actually. We'll look at just some pictures. Does the system have a Lyapunov function? We are also going to talk about a Lyapunov function for an equilibrium point based on quadratic forms. But before we get there, does this system have a Lyapunov function? Yes, though it doesn't quite fit our previous definition of a Lyapunov function. The derivative will equal 0 for a continuum of t's for the periodic solution. So that doesn't quite fit where we were looking at the derivative of the Lyapunov function only equaling 0 at a discrete set of t's and is negative elsewhere. So it doesn't quite fit that, but it basically does. The derivative of the Lyapunov function along solution curves, if you're not on the periodic solution, is going to be negative. Strictly negative. What function should I pick? It's kind of hard to figure out. Here's the function I picked. And with a bit of thought, you could reason out where I got this, perhaps. This is a quantity that's going to equal 0 when x squared plus y squared equals 1 along the unit circle. It equals 0. It's positive everywhere else. The further you go away from the unit circle in either direction, the bigger it gets. The derivative along solution curves, because they're going toward the unit circle, will be negative. That's the motivation for this, but I need to verify it symbolically. Along the solution curve x of t comma y of t, which, by the way, you can figure out the formula in this case because you could solve the differential equations for r and theta as functions of time and then convert that to functions of x and y as functions of t, using the fact that x is r cos theta and y is r sine theta. But I'm not bothering to do that here. Just use the multivariable calculus chain rule as we've been doing with Lyapunov functions and Hamiltonian functions. The derivative with respect to time of L along a solution curve, I'm assuming x of t and y of t solve the differential equation, gives me this, in general, because of the multivariable calculus chain rule. dx dt, though, by the previous slide, or maybe it was 2 slides ago, I forgot, is x minus y minus x times square root of x squared plus y squared, which I'm just writing as r. And dy dt is x plus y minus y times square root of x squared plus y squared, which I'm abbreviating as r. It's just an abbreviation here to use the r's. I'm also using r squares because they're the same as x squared plus y squared. What have I done here? I really have taken these derivatives. Double check it. The derivative of L with respect to x. Bring the 2 down in front. You get 2 times x squared plus y squared minus 1 to the first power. Times 2x because of the chain rule. That's where the extra 2x comes. I went ahead and replaced x squared plus y squared with r squared because they are equal. Think of r squared as just a shorthand for x squared plus y squared. Think of r as just a shorthand for square root of x squared plus y squared. I also need, again, to replace dx dt and dy dt with what they equal in terms of the differential equation. Now simplify. It's a bit tricky. 2 times 2 is 4. R squared minus 1 is in both terms. I factored it out. I also factored out a 4 in both terms. What am I left with after factoring out? I'm left with this. Double check it all. Pause the video, take the time to check it. You get a bit of cancellation. Negative xy cancels with plus xy. X squared plus y squared is the same as r squared. Minus x squared r minus y squared r is the same as minus, in parentheses, x squared plus y squared times r, but x squared plus y squared is another r squared. You ultimately get an r cubed. And then with a bit of creative factoring, you can factor out an r squared there and out of there, leaving you with just an r to the first of 1 minus r. And that can be written as r minus 1 with a negative sign out in front. And if you think carefully about it, this quantity is indeed negative when either r is between 0 and 1 or when r is bigger than 1. It equals 0 when r equals 1. It's also negative when r is bigger than negative 1, but I only care about positive values of r. This indeed is negative for those values of r. So the derivative of solutions of L with respect to t along solution curves is negative when I'm not on the unit circle, just like I said it would be. It's informative, and maybe even fun, to view solution curves as lying on the graph of the Lyapunov function. What? And seeing, when we do, that solutions run downhill along the graph of the Lyapunov function in three-dimensional space. I'm going to graph this function with its domain being the xy plane and its vertical direction, z, being the output of it. See a surface graph, plot the solutions on that graph, take them from the xy plane and translate them upwards to the graph of L. What will I see? I see something like this. Isn't this cool? Isn't it fun? These different solution curves in pink, orange, blue, cyan are going downhill toward that periodic solution on the circle of radius 1. Even the solution that goes toward the circle from starting close to the origin is actually going downhill, though it's hard to tell. If you zoom in closer, you can see it better. And I made a black dot at the equilibrium point at the origin. I did not put the nullclines in here. I think that's really cool, very pretty. And that's a way to geometrically view what's going on with Lyapunov functions. Very nice. This is especially apparent when you consider gradient systems, because then the solutions also go downhill as fast as possible. Here they're not going straight downhill, they're not going downhill as fast as possible. But the value of L, notice the vertical axis is labeled with the function value, is decreasing along solution curves, except at the equilibrium point and also except at the periodic solution of radius 1 centered at the origin. Okay, pretty cool. All right, here's our second main topic, and this is all in one slide, but there's a lot in the slide. Lyapunov function for a linear system with a real sink. We're going to see an application of quadratic forms. Okay, we talked about quadratic forms recently in the B lectures. Now I'm applying it in an A lecture. I did mention it's useful for differential equations. Here's one example where it's useful. Constructing a Lyapunov function. And constructing Lyapunov functions is more than just an academic exercise. It is somewhat of just an academic exercise for these examples, but it is more important for nonlinear systems. But we can't understand it for nonlinear systems unless we understand it for linear systems. Okay? With nonlinear systems, you have to use the Jacobian matrix as well. Here's our example. A linear system, dy dt is a times y. There's a typo here, there should be a y right here as well. This is the matrix A right there, times y, our typical kind of looking linear system in 2 dimensions. What do we always do? We want to find the eigenvalues, excuse me, and the eigenvectors, maybe diagonalize it, maybe use matrix exponentials. I'm not going to use the matrix exponential here. There's the characteristic polynomial. You can factor it like that. The eigenvalues are obviously -2 and -5. 2 negative eigenvalues, real. The origin is going to be a real sink, a non-spiral sink. You can take the time to check. The eigenvectors are, well, for -2 it's 2, 1, and for -5 it's 1, 1. You can have straight line solutions along those eigenvectors. I'm about to diagonalize. I should keep the y there. I'm about to diagonalize this. And when I diagonalize it, I'm going to get a gradient system. And remember, gradient systems always have Lyapunov functions. In fact, they're the opposite of the potential function. When you diagonalize it, you do get an uncoupled system. Completely decoupled is another way to say it. There's my change of coordinates matrix. Notice the columns are the eigenvectors of A. That's P. P inverse AP will be a diagonal matrix. Our theory from previous lectures guarantees that. You can double check this calculation. I actually didn't check it. I just know it has to work. But the theory, I get a diagonal matrix with the eigenvalues on the main diagonal. Hopefully I didn't make a mistake. You should double check to make sure I didn't make a mistake. The corresponding system in the new UV coordinates, you can write in scalar form like this. du dt is negative 2u, dv dt is negative 5v. You've got a completely decoupled linear system. And that is a gradient system. This system is gradient. Why? Remember the quick condition to check to see if you've got a gradient system on the entire plane. Does the partial derivative of the first function with respect to the second variable always equal the partial derivative of the second function with respect to the first variable? In this case, they do. They're both 0. This system is not a gradient system. The derivative of the first right-hand side with respect to the second variable does not equal the derivative of the second right-hand side with respect to the first variable. Again, that's the thing to check for whether something is a gradient system on the entire plane. That's not gradient, this is. Does that seem right? Should that happen? It can happen, okay? It can happen that your original system involving your non-diagonal matrix A is not gradient, but with the diagonal matrix it will be gradient. And it's going to have a Lyapunov function that's the opposite of the gradient, of the potential function. You find the potential function by integrating this one with respect to u, this one with respect to v. You'll get negative signs. Putting a negative sign in front of all that gives you positive signs. I'm calling it LD because it's the Lyapunov function for the system whose matrix is D, this diagonal matrix right there. Could I use this to not make this system gradient, because it's not, but instead to create a Lyapunov function for the original system that is not gradient? You might wonder if you could, maybe by changing variables back to x and y. How would we do that? Here's the key step right here. Let L sub A of xy, my proposed Lyapunov function for the original system with matrix A, use the Lyapunov function for this system here, the completely decoupled one that is a gradient system, L sub D, replace u and v in that formula with how they depend on x and y. I'm abusing notation there. Here u and v are variables, here u and v are functions of x and y. Don't worry about it, not a big deal. But what are those functions? Remember, when you change coordinates, y equals pu, and therefore u equals p inverse y. What's p inverse? It's this matrix. What's its first row? 1, negative 1. When you multiply times xy, you get x minus y. What's its second row? Negative 1, 2. When you multiply times a column vector x minus xy, you'll get negative x plus 2y. U does equal x minus y. V does equal negative x plus 2y under this change of coordinates. In this formula here, replace u with x minus y, replace v with negative x plus 2y. I'll leave it as an exercise for you to check that this simplifies to that. Now that is a quadratic form. And in fact, you could even say it's a positive definite quadratic form because this one's positive definite. However, its positive definiteness is not really what we're after here, because we want to verify that we've got a Lyapunov function here. Does this work? We need to differentiate this along a solution curve for the original system. And the ending answer that we get from the differentiation will be a quadratic form that will actually be negative definite. And that's why this function is going to be a Lyapunov function for the original system. Here are the details. Differentiate LA along a solution curve for the original system. There's the chain rule. The derivative of L with respect to x, I need to differentiate this with respect to x. I'm going to get 7x minus 12y. That's what you see there. The derivative of L with respect to y is right there. Differentiate this with respect to y. You get negative 12x plus 22y. That's right there. dx dt for the original system is x minus 6y. Notice the first row of A. dy dt for the original system is 3x minus 8y. Notice the second row of A. Multiply that L out, you get this. Double check that. Take the time to do that. That's also a quadratic form. It's going to be negative definite. It only equals 0 when x and y are both 0. It's negative otherwise. This is going to be a Lyapunov function. Its derivative along solution curves will be negative. The symmetric matrix that defines the quadratic form, I used Mathematica. I found the eigenvalues to be approximately these two numbers. They're both negative. By a theorem, that means that quadratic form is negative definite. That does it. We're done. That verifies the derivative of the LA along the solution curve is always negative when you're not at the origin, when you're not at the equilibrium point at the origin. Okay? And I could graph L as a function, LA as a function of x and y, and I could graph solution curves on top of it. In fact, I did that on Mathematica. I'm not sure if I'm going to have time to show you. And solutions would go downhill. Keep in mind here, everything does depend on t. You don't see it in there explicitly, but we are talking about derivatives along solution curves. But you don't need to put it in there, because this is going to be negative whenever you're not at the origin, no matter what t is. It doesn't matter. That's why you don't need to put the t's in there. Just keep in your mind that you are differentiating along solution curves. All right, lots of information on this slide. On to our last topic, Laplace transforms. There's going to be 3 slides here. Can't get into a ton of details. This is a big picture overview with some details. Okay? Lecture 35A will definitely get into more nitty-gritty details. Suppose, for the sake of argument, that there is a transformation, an operator, L, that's an L, cursive L. By hand, I will make it like this. Isn't that pretty? Cursive L. From one function space to another function space. The inputs of this transformation are going to be functions of t. The outputs are going to be functions of s. Why t and s? Well, the t is because we usually use t as the independent variable for differential equations. The s is just an arbitrary letter to pick. Somebody picked s. I guess Laplace picked s, and so we're stuck with it. The transformation needs to be linear. Same meaning of linear as always. L of a linear combination is the corresponding linear combination of the functions, f and g. I'm using square brackets here instead of parentheses. That's just an arbitrary choice, but it is somewhat traditional for the inputs of this function L. This is true for when alpha and beta are any real numbers, for all such real numbers, and for all appropriate functions f and g. They're going to be functions of little t, but I'm not putting little t in there explicitly. I do sometimes, but not always. That's what it means to be linear. Operation preserving. Alpha f plus beta g is a function. L of that is another function. This entire thing is another function. I want it to be invertible with a linear inverse transformation as well. L inverse must exist and satisfy operation preserving property as well. Here, once again, alpha and beta are arbitrary real numbers, and f and g are arbitrary appropriate functions. I'm not saying what appropriate means. It is traditional to use lowercase f and g here and uppercase f and g here, but you don't have to. I also want, it turns out, the transformation to convert differentiation to arithmetic. Algebra, you might say. as follows, according to a very particular rule. This rule is very particular, kind of strange. The derivative of L of the derivative of a function of t is a function of s whose formula is this. S times the Laplace transform of y itself. Y is a function of t. I'm not putting the t in there explicitly. Minus y of 0, the function evaluated at 0. For all appropriate functions, y equals y of t. What a weird thing to do. It's useful. Such a transformation might help us transform a linear differential equation initial value problem to an algebra equation that we might be able to solve and transform back. That's the big picture of how to use Laplace transforms. It's a very different subject than everything else in this course, by the way. If it's not clear so far. So I'm going to show you a differential equation. There it is. Made it first order to keep it simple. It is linear. We've seen this kind of equation before. We've solved it before, like either with integrating factors or method of undetermined coefficients back in chapter 1. What if I now took the Laplace transform of both sides? Assuming everything is a function of t on both sides, y is an unknown function of t. This is its derivative plus 5 times itself. The right-hand side is a known function of t, e to the negative 2t. I've also got an initial condition there. If I take the Laplace transform of both sides and use the linearity as well as this property, I get this on the left side. It's a couple steps there. I'd have L of dy dt plus 5y. By linearity, that'd be L of dy dt plus 5 L of y. The 5 L of y is right there. But L of dy dt by this property is equal to what you see right there. If I apply L to the left side, I've got to apply it to the right side too, so I have this on the right side. Whatever that happens to be. I'm not saying yet what that is. What's the goal again? The goal is to solve for y. If we could solve for L of y, this is just an algebra equation in the unknown L of y, and then apply L inverse, we'd get back y. I could write it like this. Y is L inverse of L of y, but L of y is this entire thing. If I solve this for L of y by first adding y of 0 to both sides, which is 3 by the way, and then dividing both sides by s plus 5, because L of y appears there and there, I would get this. Exactly what I circled over there. Huh. So if I could figure out the stuff inside the fraction, and then I could figure out L inverse of that, I guess I'd have y. It's not so clear that this is very easy, or how to do it, but now let's go into the definition of the Laplace transform. Hang on, I'd like to drink of water. Oh, and there's our vacuum. What is the definition of Laplace transform? It's weird. Does such a Laplace transform exist? First of all, is there a function cursive L that satisfies all these properties? Well, of course, otherwise we wouldn't be talking about it, ha ha ha. It's defined by the following improper integral. What? When the improper integral converges. Improper integral? Are you kidding me? No, I'm not kidding. This is similar to Fourier transforms too. There are other transforms that are defined by integrals. It's this improper integral. Essentially right here. Capital F of s is my output function. When I plug in little f of t, I could have put the of t in here, but I didn't. It's a function of s. It's defined to be this integral when the integral converges. This integral, when I do it with respect to t, does depend on s. The value of s affects the answer, and it changes as s changes. Technically speaking, by definition of improper integral, it's a limit as b goes to infinity of proper integrals where that b there is finite, but then I'm letting b go to infinity. To converge means this limit exists. This is definitely a linear operator because integration is linear. I'm not going to verify that, but you've seen before the integral of a sum, for example, is the sum of the integrals, and that does apply to improper integrals when they converge. That evidently takes a sufficiently nice function of t, the little f, and gives a function of s, the big F. Does it convert differentiation to arithmetic? Yes, it does. We can use integration by parts to verify that. Here are the details with a little bit of hand waving here. The L of a dy dt, by definition, is the integral from 0 to infinity of dy dt times e to the negative s t dt. Just using that formula there, with y prime in place of f. If you look at this long enough, you realize this is something you can use integration by parts for. If you let this thing be u, and y prime of t dt be dv, or if you prefer, y prime is v prime, if you're used to doing integration by parts that way. This is u, this is v, u times v minus the integral of v times du, plus s e to the negative s t dt, that's the du, not showing up, du, and y of t, that's the v. uv minus the integral of v du involves a negative sign from differentiating this, but in the integration by parts we subtract there, so the negative signs combine to give a plus. I can factor the s out of the integral because the integral doesn't depend on the integration variable is t. So s is constant with respect to t. But wait a minute, this integral is nothing other than L of y. And I got an s in front of it. What about this thing? I claim that equals negative y of 0. But isn't there a limit I have to calculate? Got an infinity there? Well, this works if we assume that this limit is 0. When I plug in infinity, so to speak, I better get 0. When I plug in 0 and subtract e to the 0 is 1, I get minus y of 0, which gives me the negative y of 0 there, as long as this is true here. And that will be true as long as y of t does not grow too fast. Then this limit will be 0. So we do restrict ourselves to input functions that don't grow too fast in the Laplace transform. Whatever that will mean, I won't need to really worry about it though. Last slide. We also evidently need to know the Laplace transform of particular functions, like if we're going to solve the differential equation is what I'm referring to, like e to the at. In the differential equation, a was negative 2. By definition of the Laplace transform of e to the at is this integral. There's my f of t. Pretend s is a constant as you do the integral. T is the variable for the integral. You can write it like this, which by definition would be this. Taking the limit as b goes to infinity, the limit will exist when s is bigger than a, so that s minus a is positive and negative of s minus a is negative. And it will equal, you can check, 1 over s minus a. As long as s is bigger than a, and now we can think of that as a function of s. We can change our perspective and think of that as a function of s. This is going to be good to know, because it's going to help us solve our differential equation. This particular fact also means when a is 0, since e to the 0 is 1, that the Laplace transform of the constant function 1 is 1 over s minus 0, or just plain 1 over s. So a is 0 here. I'm using the previous line. Since in the example we've got this equation, this was what we saw before, I can replace L of e to the negative 2t with 1 over s plus 2. A is negative 2. 1 over s minus a would be 1 over s plus 2. Y of 0 is 3. Then I can simplify this fraction and break it apart into pieces. I got a piece 1 over s plus 2 and also over s plus 5, which is what you see there. I've also got the 3 over s plus 5. I can factor the 3 out because L inverse is linear and have this. So we would need to find these inverse Laplace transforms. I'm not doing that here in lecture 34a. we'll do it in lecture 35A. But if I can find those, then I would be done. Is finding these inverse things easy or hard? Well, this one's easy. In fact, look up here. You're going to go backwards, e to the negative 5t. Sorry, that's not coming out. E to the negative 5t. That one's harder, though. I bet you could guess what we would use, though, to help us do it. Can you guess? Partial fractions will help us figure this out, which you've used for integrals before. You can also use it now for inverse Laplace transforms. Let's quickly end lecture A by looking at the Mathematica. Again, this can be found on the Google Drive. I'm not going to describe all these details, but suffice it to say, here I'm trying to solve the system in polar coordinates. Here's what the solution curve for the first example looks like in our theta plane. Remember, I drew this kind of picture on the board. And then we convert to the xy plane. And I allowed myself to use the locator to change the initial condition. Oops, I need to enter some things here. Excuse me. There we go. Now I can change the initial condition point, move it around, but no matter what initial condition you start with, except at the origin, you're going to approach the limit cycle along the circle of radius 1 centered at the origin. And I also do have code to make the three-dimensional picture that I showed you, and code to look at the Lyapunov function for the linear system example and see that its solution curves go downhill. I didn't show you this before. Okay, so this is the Lyapunov function for the linear system with an equilibrium point that's a real sink at the origin. I've graphed the solutions on the graph of the Lyapunov function. You can see them going downhill toward the origin, which is at a minimum. Okay? I think that's pretty cool. Hope you do too. Thanks for watching.